Okay, in this video we're going to look at orthogonality of functions. So let's begin with a definition here. So two functions are said to be orthogonal in some interval AB. So we're going to denote our two functions phi m and phi n. M and n are typically integers, so these two functions are said to be orthogonal in the interval AB with respect to what we call a weight function w of x if they satisfy the following condition. If this quantity here wx phi m phi n dx, if this quantity is equal to 0. All right, yeah, so this quantity is 0 whenever m is not equal to n. Let's call this equation number 1. This quantity is called the inner product of phi m and phi n. Called the inner product is actually a generalization of the dot product remember that if the dot product of two non-zero vectors is 0, then those two vectors are orthogonal, are perpendicular to each other. Now the set of functions phi I so this set of functions is called orthonormal in AB with respect to the weight function W if in addition to 1 the following hold. So if the inner product of phi n phi n, which is w times phi n squared. So if this is equal to 1, then we say that the function is orthonormal. So yeah, so these are the two definitions that we're going to present before we do some examples. Alright, in this set of examples, we are given a set of functions. We are required to show that it is orthogonal in the given interval with respect to the specified weight function. In A, we have got signs of integer multiples of x. That's our interval. The weight function is 1, so m is an integer. In B, we've got 1x and half 3x squared minus 1. You can see these are the first three Legendre polynomials. The interval of orthogonality is -1 to 1. Weight function is 1. In C, we've got these three polynomials. The interval is 0 to infinity. Weight function is e to the minus x. In D, we have got e to the imx and e to the minus inx. Same interval and weight function is A. So let's start with A. So we're going to do phi m in a product of phi m, phi x. So this is going to be the integral from minus pi to pi of sine mx sine nx. This we can integrate using the trigonometric identities, or alternatively we could write sine in complex form. So let's just use the trigonometric identity approach here. It's going to be m minus n or n minus x. It doesn't matter because cosine is even. So this is going to integrate to sine m plus m x over m plus n, and this one is going to be sine m minus nx over m minus n from minus pi to pi. Because of this term here, this we have to exclude the case m equal to n, otherwise we're going to be dividing by 0. So this thing, remember m and n are integers, so m plus n is an integer, m minus n is an integer. However, sine of an integer times pi is 0. So this is going to be 0 because sine n pi is 0 whenever n is an integer. So that shows that the set of functions sine x, sine 2x, sine 3x, etc. Is going to be orthogonal in the interval minus pi to pi. In part B, what we're going to do, so these are polynomials, we're just going to use that notation. So first, let's start with the inner product of P0 and P1. So that's just going to be the integral from -1 to 1 of x, because P0 is 1 and P1 is x. Now this is a symmetric integral of an odd function, so it's just going to be 0 without us having to do any calculations. Then inner product of P0 and P2 is just going to be the integral of P2, so half into the integral of 3x squared minus 1 dx. This is going to be the, so integral of 3x squared is x cubed. So this vanishes on either side. So when x is 1, this is going to be 0. When x is minus 1, this is going to be 0 as well. So this integral is going to be equal to 0. Then P1, P2, so the inner product of that going to be half into the integral. This time we're going to have 3x cubed minus x dx, which again is odd, so I've got a symmetric integral of an odd function, so that's going to work out to 0. So that takes care of all three of them. Okay, now we're going to go to C. In C, the first function is 1, the second function is 1 minus x, and that's the third function. We've got a weight function this time. So let's start with phi naught, phi 1. So we're going to do integral from 0 to infinity. That's the integration interval, or interval of orthogonality. So, however, these are just typical gamma function terms. So the first one, this one here, times that, it's just going to be the gamma function of 1. Then the other one is going to be the gamma function of 2. Gamma function of 1 is equal to the gamma function of 2. They're both equal to 1. So that is going to be equal to 0. Then inner product of phi naught and phi 2 is just going to be the integral of phi 2. Again, all these are going to be gamma functions. This one is going to be the gamma function of 3 minus 4 times the gamma function of 2 plus 2 times the gamma function of 1. The gamma function of n is n minus 1 factorial. So this one is 2 factorial, this one is 1 factorial, this one is 0 factorial. So it's 2 minus 4 plus 2. This is equal to 0. Then inner product of phi 1, phi 2 is going to be half into the integral of 1 minus x into x squared minus 4x plus 2 dx. Multiplying out there and simplifying, it's going to give us 2 minus 6x plus 5x squared minus x cubed e to the minus x, sorry, there's e to the minus x there, dx. And so this time we have 2 times the gamma function of 1 minus 6 times the gamma function of 2 plus 5 times the gamma function of 3 minus the gamma function of 4. So this is going to work out to 2 minus 6 plus this is going to be 10 because that's 2 factorial. This is 3 factorial, which is 6, but it's minus 6, so minus 6 there. So that's going to be 2 plus 10, which is 12, minus 6, which is 0. Right, I'm now going to give you a few minutes if you just want to take a few minutes to work this one out. Pause the video, and then when you continue the video you can compare with our answer. Okay, so we hope you have had a go at this example D. I'm now going to scroll down to a solution we're going to work out here. So this is going to be e to the imx times e to the minus inx dx. So this is e to the I m minus n x dx. This we can integrate, not a problem. M minus nx all over I m minus n. So again, m should be different from n. So from minus pi to pi. So when we plug in the limits, it's going to be e to the I m minus n pi minus e to the minus I m minus n pi all over I m minus n. Now remember that m and n are integers, so these is like e to the I, well, integer times I pi and minus integer times I pi. So you're going to recall that if this integer is even, this is 1, it's exactly the same there. This integer is odd, e to the I pi is exactly the same as e to the minus I pi. So the question that you might want to convince yourself about is this one: is e to the I n pi always equal to e to the minus I n pi? Because if that is the case, then this is always going to be 0. However, what I'm going to do here is I'm going to write this in terms of sines and cosines, and then perhaps the result is going to be a bit easier to see for some of us. So what I am going to do is I'm going to write this as e to the I m minus n pi minus e to the minus m minus n pi over 2i. The I was already there, the 2 was not there. So what I'll do is outside here I'll write 2 over m minus n. So now things are balancing out. So this is 2 over m minus n sine, this is just a sine of m minus n pi. Now since m minus n is an integer, we know that sine of integer times pi is always equal to 0. So that means that set is going to be orthogonal as well. In fact, these functions here are used to construct the so-called complex Fourier series. These ones, on the other hand, for the half-range sine series. All right, thanks for watching. I hope that this has been useful. Please do subscribe to make sure that you can get notified, and if you've got questions and comments, you can post them in the comment section, and please do share with people if you find this useful. Thank you.